Okay, good evening, everyone. So today we will discuss conditional expectation. So first, let's see what is a conditional expectation. So maybe let's recall what is conditional probability. The idea of conditional probability is like this. So we know that originally you have a sample space, which is capital omega, right? Then you know that an event A occurs. So which means that essentially your effective sample space will shrink from this capital omega, shrink into this A, typically a smaller set, right? So then, so as we discussed many times, in this case, then probabilities will change. So after you know that A occurs, then we need to discuss everything in terms of conditional probabilities, right? So not unconditional probability, but this time conditional probabilities. If we think of random variables, so what is a random variable? Random variable is a function from outcome to a real number, right? The input is outcome, the output is a real number. And we use a distribution to describe the probability behavior of a random variable, right? And so you think of this. If you know that A has occurred, right? So essentially it means that the outcome can only be within this set A. It cannot be anything, right? In this case, if you think of this random variable, you may realize that the distribution of the random variable in general will also change, right? Because your sample space has changed accordingly. So when we talk about the distribution of this random variable, we need to think of conditional distribution. I think before the recess week, when we discuss joint distribution, we also discuss conditional distribution, right? And if you know you have this extra piece of information that A has occurred, and as I said, the distribution of a random variable will also change from original distribution to a conditional distribution. And as a result, the expected value of that will also change, right? So then it's now you need to consider conditional expected value. So how to calculate this conditional expected value? I think the idea is pretty straightforward. The definition is here. So for example, if we think of so this random variable x as a discrete random variable, so then we can first think of its conditional distribution. Because it is discrete, then we can talk about the conditional probability mass function, right? So we discussed that, I think 2 weeks ago, 3 weeks ago? Yeah, 3 weeks ago. So this conditional PMF is defined like that, right? It is just the probability that this random variable takes whatever value given that A occurs. And based on this, we can define the conditional expected value of x given that A occurs. So it's written in this way, E of x given A, right? So then how to calculate that? The idea is pretty straightforward. Also, we take a summation. We sum up x over all possible values. And at each possible value, so this value should be weighted by a probability. But this time, it's a bit different from the definition of unconditional expected value. So we need to use the conditional probability, so as the weight, right? So it should look like this. I think it's the idea is pretty straightforward. So then maybe before I move on, let's think of exercise problem. So here, suppose that we have two independent Poisson random variables. We call them x and y, and they have the same expected value, so which is lambda, right? Recall that when we talk about Poisson distribution, it has only one parameter. So which means that you know the expected value of this Poisson distribution, you can determine everything, the PMF, whatever, right? So you see that because they have the same expected value, essentially they have the same distribution, and also they're independent. So here we wish to find out so this conditional expected value. So x, given that x plus y is equal to m. So this m is a non-negative integer, right? So recall that a Poisson random variable can only take non-negative integer values, right? It could be 0, 1, and so on. So the sum of two Poisson random variables will also take non-negative integers. So here, this m must be a negative integer. So how to calculate this? And actually, so this one, there are two ways. The first way is pretty simple, and the second way is a standard way. So maybe let's first go over the simple way. So the simple way is to use symmetry. So what do you mean symmetry? Symmetry means because here, so this is a very special case. We assume that x and y, they have the same distribution. They're independent, right? So as a result, if we think of so this conditional expected value, so x, given that the sum of them is equal to m, actually, so you can easily realize that it is equal to the expected value of y given the same condition. So why is so? Because the behavior of x and y are exactly the same, and they're independent, right? So whether we call this guy x or y, it does not matter, right? So if we just change their names, then you see, so this expression should look like this. So it should change nothing. So they must be equal. So this is why we must have this result. Conditional expectation of x must be equal to the conditional expectation of y. So this is the first property we just derived. And then, so let's think of the sum of those two guys. So this one, if we sum of them up together, right? So this is this conditional expected value plus so this conditional expected value. Then, because if you think of conditional expected value, so based on the definition on the previous slide here, so essentially you see that it is just still a weighted sum of all possible values with a probability as the weight, right? So then, based on this expression, you can easily realize that so this conditional expectation should have all properties as the regular expected value, right? Because of this. Because as we explained, conditional probability should satisfy all the properties unconditional probability should satisfy. And because of this, so conditional expectation also have this the so-called linearity property. So if we take the sum of those two guys, actually, because they're under the same condition. So this one must be equal to the conditional expectation of x plus y given the same condition, right? So this is the second property we can derive. And then let's observe this. So the condition is that x plus y is equal to m. And then, so because this is given, so which means that x plus y must be a constant, which must be equal to m, right? So then if you take expectation or whatever, it does not matter because given this condition, so this x plus y must be equal to m. And because of this, so then this guy must be equal to m, right? So you see, we have two values. So those two values are equal, and the sum of them is equal to m. So each of them must be equal to m over 2, right? So this is the simple way of calculating this using symmetry. So as I said, there's another standard way to show this. So then in the standard way, we need to find out the conditional distribution of x, right? It could be a bit complicated, but it's as I said, it's standard. You just follow the definition of conditional probability, and you derive things. So we can derive things like this. I think then I will just leave things to you, and you just follow this formula, and you can calculate this. So and then you will reach the same result, m over 2. But I think I will not discuss the details. I will just leave it to you. So please check the details after class. So this is an example. So then let's change the setting a little bit. So here, so this time, previously we consider the conditional expectation given an event, right? So this time, let's think of a special event. So what is that event? So here, we consider two random variables, x and y, right? Suppose both of them are discrete. And then suppose that we know the PMF of y. So it looks like that. And then, so based on this, if we know the joint PMF of both random variables, so we can derive the conditional probability mass function of x, given so the random variable y takes whatever value, right? So this is something. This is also something we discussed 3 weeks ago. And then let's think of this conditional expectation. So this time, the event takes this form. So this event just the random variable y takes value lowercase y. It is an event, right? So because it is an event, then we can just follow the definition we just introduced to give the expression of this guy, right? So in this time, we also need to sum up all possible values this random variable x may take. And so this each possible value should be weighted by the conditional probability, right? So then this is the conditional expectation of x given that another random variable takes a value. So this is so such a conditional expectation. I think it's also very easy to understand. So maybe this is for the discrete case. And also we can define conditional expectation for continuous random variables in a similar way, right? So the only difference is that So this time for continuous random variables, we need to take an integral instead of take summation, right? So then what we need to do is just something like this. If the condition is still a continuous random variable y takes whatever value, so this conditional expectation should be an integral over the entire real line, right? And at each point, so it should be weighted by the conditional PDF, right? So then what is the conditional PDF? Before the recess week, we also introduced that. It is simply the joined PDF over marginal PDF of y, right? So this is the conditional PDF. If you cannot remember it clearly, so you need to go back to check our lecture notes or textbook. So this is the conditional expectation of continuous random variable, right? So given such a event. So, and actually, I think so far everything seems regular, right? And as I just said, conditional expectation actually satisfy all properties ordinary expectation should have, right? Because essentially, you know that an event has occurred. You just change the sample space a little bit. So within the new sample space, because it is still a probability space, so then all the properties of expectations should still be there. So for example, I think you need to be very clear about several properties. So for example, if you wish to calculate the conditional expectation of a function of a random variable x, given the condition that a random variable y takes a value, then what you need to do is just to follow what we learned for expected value of a function of a random variable, right? So how can we calculate this thing? We just, for example, if x is a discrete random variable, we just take a summation over all possible values so this random variable x may take, right? At each value, we need to evaluate the function g at this value and weighted by the corresponding conditional probability, right? And for continuous random variable, if this x is a continuous random variable, we just take integral instead of summation. But the idea will just be the same, right? And also, as I said, for conditional expectation, it should also have a linearity property, so which is the following two properties. So which means that if we wish to know the conditional expectation of a times x, given whatever condition, this a is a constant, then this constant can be taken out, right? And linearity has another part, so which says that if given under the same condition, the expectation of the sum of two random variables should be equal to the sum of their respective conditional expectations, right? So actually, when we discuss this, we have used this property. So this is something, I think it's pretty similar to what we discussed previously. So before we move on, maybe let's check a very simple example. So suppose we have two discrete random variables, x and y, right? And their joint distribution follows this table, right? So you may have recognized this example. So this example, actually it's just my food and drink example, right? So over lunch, I can spend either $2 on food or $4 on food. I can spend either $1 or $2 for drink, right? And their joint distribution follows this, so this table. And I think in the past, we also derived the conditional distribution of this little example, right? So for example, if I know that, so over a lunch, I spend $1, then what is the probability that I spend $2 on food? What is the probability that I spend $4 on food, right? So how to calculate that? So I think I mentioned that if you know that, so y takes value 1, then the conditional distribution should be determined over this column, determined only by this column, right? So the second column does not matter. So I think I mentioned that before the recess week. So for example, what is the probability that I spend $2 on food given that I spend $1 on drink? So it should be, so there's 0.6 over the sum of this column, because the sum of this column gives this marginal probability, the probability that y takes 1, right? So, and so on. So this is this is what we discussed 3 weeks ago. So for example, in this example, I may wonder if I know that I spend $1 on drink, then on average, how much I would spend on food, right? In this case, as I said, actually it becomes a conditional expectation, right? So it would be this guy. If I spend $1 on drink, then on average, how much I would spend on food. How to calculate that? So we may just use so those results. So if I spend $1 on drink, I may spend $2 or $4, right? $2 with probability 1 and $4 with probability 0. So this conditional probability is just $2. And also, similarly, if I wish to know what is the conditional expectation of x given that y takes 2, then so it should be determined by this column, right? So I think it's it's pretty clear. So even if so this example is very simple, but I think you need to keep in mind that if we wish to know the conditional probability that so this random variable y takes 1, so then everything should be determined by this column, right? And if you know this random variable y takes 2, everything should be determined by this second column. So you must be very clear of this, right? So then, so please keep this in mind. Then let's think of a problem like this. So here, as I explained in the previous example, so when we wish to know a conditional expected value of x given the event that random variable y takes a value, so then we can either follow this expression or this expression, depending on whether this random variable x is discrete or continuous, right? And as I said just now, so in this example, if you know the value, so this random variable y takes, So essentially, you need to only use one column to determine the conditional expectation of x, right? So in this example, it boils down that whether you use this column or this column, you have only two columns. Why you have only two columns? Because this random variable y only takes two different values, right? So then you may realize that in this case, actually when we think of the expectation of x, given random variable y takes whatever value, so this is a lowercase y, then this guy, this conditional expectation of x, is indeed a function of the value this random variable y would take, right? Why said so? Because essentially this y just determines this column or this column. You fix this column, then you do everything based on the information provided by this column. Everything is fixed. You have a deterministic number, so which is that conditional expectation, right? So you see that, so even if this example, as I said, is very, very simple, but actually it helps you to visualize how this conditional expectation works. So you specify the value of random variable y, you just specify a lot of values. Each value corresponds to a column or whatever things. And you use the information over this column to calculate expectation, right? So I think so far it's clear. So now what you really need to keep in mind is that this conditional expected value of x is a function of the value this random variable y takes. So again, what does it mean? It means that the conditional expected value of x depends on the column you take, right? You take different columns, so this conditional expectation may have different values. So as I said, then, so this conditional expected value becomes a function of the value corresponds to different columns. So now, if you think if you're clear of this, then I think the next step will be very easy. So because you realize that there exists a function, maybe we call this function h. So what is the definition of this h? This h of y, lowercase y, is simply expected value of x, given that random variable y takes value this lowercase y. So as I said, so this conditional expected value is a function of the value this random variable y takes. So keep this in mind. Then let's think of something like this. So this conditional expected value becomes a function of the value this random variable y takes, right? How if we don't know the value y would take? Y is a random variable, right? It may take 1, it may take 2 in this example, right? So how if I wish to know, so what is the expected value of x given y? So this y is the amount of money I spend tomorrow for my lunch. Tomorrow I may spend $1, I may spend $2. So far, I don't know, right? So in this case, you can see that actually if you don't know the value this y would take, then we may think of this conditional expectation as a function of a random variable. So this random variable y may take 1, may take 2. If it takes 1, so this conditional expectation will be equal to 2. If it takes 2, it will take value 3.25. But if you don't know the value this y would take, then it will become a random variable. What is this random variable? This random variable is just a h of y. This y is a random variable. A function of a random variable is again a random variable, right? And how to define this function h? This h is defined in this way. So this part could be a bit confusing for some students. Why I said so? Because in the past, when we talk about expected value means it should be a deterministic number, right? So when we talk about the expected value of x, so as long as you know the distribution, then you can calculate that. It's a fixed number. It's no randomness at all, right? And if you know the event, whether this event is any arbitrary event A or y takes whatever value, then such a conditional expectation is also deterministic. Why is so? Because you know the event. You know an event has occurred. Essentially, you know the set of all possible outcomes. Then you just do whatever regular or ordinary expectation to calculate this conditional expectation. But when we write something like this, expectation of x given y, here it means that we don't know the value this random variable y would take. Then the meaning of this notation is a function of the random variable y. Because y is a random variable, a function of a random variable is again a random variable. So this thing is a random variable. A may take this value or this value, right? So in this example, we know that y is equal to 1 with probability 0.6, right? So if we think of E of x given y, then with 0.6 probability, so this guy will be equal to 2. With probability 0.4, it will take value 3.25, right? So this is the conditional expectation. So about this conditional expectation, so there's a very useful result like this. So this result could be could seem confusing at first glance. So here, let's consider two random variables x and y. And this proposition says that the expectation of x is equal to the expectation of the conditional expectation of x given y, right? So this one, I think some of you may feel a bit confused about this notation, how to understand this. Actually, the interpretation of this this proposition, I think, is here. So we just discuss. I just give you the detailed interpretation of this result when y is discrete and continuous. Maybe let's check the discrete case. If y is a discrete random variable, then this proposition says something like this. Maybe let's check the right-hand side. The right-hand side is this guy, right? Then it's the expectation of a conditional expectation. So first, how to understand this? So first, we need to think of this thing. So first, this conditional expectation should be understood as a function of a random variable, y, right? So this thing is a function of a random variable, y. So because of this, so let's write this conditional expectation of x given y as h of y. H is a function. So it makes sense to talk about the expected value of a function of a random variable, right? We discussed that many times. Then for this one, the question is how to calculate that. And we have learned this many times, right? So this one, we just follow the general formula. We just, because this y is a discrete random variable, we just take a summation over all possible values it may take, right? So then at each value, we find out, so what is the value of h of y and times the corresponding probability. And then we have this thing, right? Then the question is, what is this h of y? H of y is defined here. It is also a conditional probability. Conditional probability that given that random variable takes a fixed value. So this guy actually is equal to this one, right? So then what is the meaning of the right-hand side? For the discrete case, it just means that it is the meaning. And for the continuous case, I think it's similar. You only need to take an integral instead. Everything else will be just the same. The idea is just the same, right? So this is the interpretation of this result. So, and this result actually is pretty simple to prove. So maybe let's go over to see how to prove this. So first, so maybe let's just consider the case that y is discrete. If y is discrete, as I explained just now, this result simply means the expected value of x is equal to this expression. That is the meaning. So that is the meaning of this thing. So we need to show that this guy is equal to the expected value of x. So that's the purpose of our proof. So then let's see how to prove this. So let's consider the right-hand side first. The right-hand side looks like that, right? It's a conditional expectation times the probability about random variable y, right? And then maybe let's first think of how to calculate this conditional expectation. So this one, I think, is pretty simple because we discussed that at the beginning of this lecture. The definition is here, right? If you wish to calculate such a conditional expectation, you just follow this formula. So this guy, we need to take a summation over, because it is a conditional expectation of x. So then we just take this summation. Take a summation over all possible values random variable x may take, and each possible value. So it should be weighted by conditional probability, right? So then you see here, so this part is this a conditional expectation. So then we have this such expression. So this expression is pretty nice because you see that this conditional probability times the probability that y takes a value, then it becomes so this probability, the probability of intersection of those two events, right? Then from here, we have here. So then, so this is about a double summation. So first summation is about x, and the second time we need to take summation over y. But we can change the order of summation. Because, so here, there's a x in, so if we change the order of a summation, then we can, if we take the summation over y first, then this x can be taken out, right? So summation of y of so such joint probabilities. So because this is summation of all possible values of y, you know the joint probabilities, joint distribution, take the summation over all possible values of y, what you have is marginal probability for y, right? That's the definition for marginal probability. So from here, actually, so this summation you have, it is exactly the probability that x takes value lowercase x. Then if you check this expression, what is that? It is exactly the expected value of x, right? So, so this one, actually, it's not difficult to understand. So why I said so? Because it just specify a way for calculating this expected value of x, right? So as I said, so this guy is equal to this y. So here you may think of this result in such a way. X and y, they may depend on each other. If y takes whatever value, it may change the distribution of x, right? So you may know some information about y first, right? And then based on, if you know something about y, it may help you to know more about x. So then, so what you need to do is just to think of different cases in which y take different values, right? So if y, so this random variable y takes a whatever value, then you know that the probability, the corresponding probability should be this one, right? Probability that random variable y takes a value. When the value of y is fixed, so then y, you know the value of y, then it may help you to calculate the expected value of x. But this time, it becomes a conditional expected value, right? So in this way, you know this value. But you need to realize that, so for different values, y may have different probabilities. So such a probability should become the weight for such a conditional probability. Then you just think of, you sum up over all different cases with correct weights. Then overall, you should have the expected value of x, right? So that's a very intuitive interpretation of this result. And actually, you may have realized that that's exactly, so what we proved here. That should be the same thing, right? So this is this result. As I said, it's a very useful result, because as I said, the moral of that is if it is not easy for you to calculate the expected value of x directly, because you may not know the distribution of that, right? It may depend on another random variable. Then it will be better for you to discuss case by case. If y takes this value, so what will be the conditional expected value of x? If y takes that value, what will be that? And you discuss case by case, and in the end, you put them together, right? So that's the idea. So maybe, so let me show you an example so that you can understand this idea better. So here, so we consider a sequence of IID random variables. Again, IID means independent, identically distributed. Independent means that they have nothing to do with each other. Identically distributed means they have the same distribution, right? They have the same distribution, they should have the same expected value. So assume that each of them has the expected value mu, right? Then, so there is another random variable. We call it capital N. So which takes a positive integer value. It could be 1, 2, and so on, right? Then we assume that this N is independent of the sequence of X. And we assume that expected value of this random variable N is equal to this lowercase n. Then we wish to know the expected value of this guy. So what is this guy? So first, it's a sum, x1 plus x2 plus x3. But the number we take from x is random. We take from x1 up to x sub capital N. If n is 5, we take 5. If n takes 7, we take 7. Right? So you see that it's a sum, but the number of x is random. So we need to think of the expected value of this guy, right? So let's see how to calculate this one. So essentially, what we wish to know is something like this, right? You may realize that it's not easy to calculate that directly because you don't even know how many x you need to think of, right? It could be 1, it could be 2, and so on. So maybe let's first think of a simpler case. So suppose that we know that this n takes a fixed number. Then let's see what will happen for here, right? Say, given that this random variable n takes value j, so this j is a positive integer, then what is the expected value? So it's written like this, right? Because the condition is that n takes value j, so actually when you calculate this sum, you only need to sum up x1 up to xj, right? So from here, you have something here. So we just replace this n with j. So then, next step, because if we think of this, how to calculate this? In this example, we assume that this n is independent of all those x, right? So which means that whether you know the value of n, it won't affect the distribution of each x, right? Whether you know, so this n is this or that, it does not matter. If it does not matter whether we keep this condition or not, it makes no difference, right? So this is a pretty simple but pretty important step. Because if they're not equal, then it could be, if they're not independent, then how to calculate this could be an issue. But if they're independent, then we can simply discard that. We don't consider that, then this one becomes pretty simple, right? Expectation of j such guys. Each guy has expected value mu, so this one must be equal to j times mu, right? So this is the case that you know the value of n. You know that it takes value j, then this guy, this conditional expectation is simply j times mu. Here, then this is the first step. So this is a, so this one actually, so this is a random variable. So the condition is about a random variable takes whatever value, right? So then, as we explained here, this thing should be a function of the value this n takes, right? So this n takes the value j, so this one should be a function of j. So we know the exact form of that is a mu of j. But you need to keep in mind because it will help you to understand the next step. So maybe it's more convenient for you to think of this as h of j. Why is so? Because next step, this n will become a random variable, right? So let's think of this as h of j. So if this guy is a h of j, again, as I said, this h of j actually is defined as this thing. When n takes value j, this guy is called h of j. So again, if we don't know the value n takes, so then this one should become h of n, right? You know the value n takes, then you know the value of this guy. If you don't know the value, then it is just a function of a random variable n. So then the question is, what is the form of h of n? If we know that h of j is this guy, then h of n should be simply n times mu, right? So as long as you're clear of this, then I think the next step would be simple. This is something we wish to know, we wish to calculate, right? How to calculate this? As I said, we may just need to discuss case by case. How if n takes 1, how if n takes 2, and so on, right? But because we already know this, right? So then this guy we may just think of this one in this way. If we think n takes different values, then so this one should be equal to this. So this conditional expectation, as I said, it is simply a function of n, random variable n. And here we just argue that so this function should take this form, n times mu, right? So because this guy is n times mu, so this whole thing should be expectation of n times mu. Mu is a constant, we take it out, right? And we know that expectation of n is equal to this lowercase n. So in the end, it's n times mu, right? So this one is not difficult. But if you don't know how to handle this, I think if you wish to calculate this directly, it may not be that easy, right? Questions? So I think I may also mention another technique that is that is often used when solving problems. So actually, it is just a special case of this thing. So this thing says that expectation of x is equal to the expectation of a conditional expectation. And as I said, the principle of this thing is that, so this x may depend on y. It could be more convenient for you to discuss different cases when y takes different values, right? So sometimes you may be interested not the expected value of a random variable, but would be the probability of an event. So then the idea, so how to use a similar idea to deal with such a situation, right? And actually, the idea is to introduce an indicator random variable. So let's recall what is an indicator random variable. So indicator random variable, I think when we introduced that, so we discussed that first it's a Bernoulli random variable, right? It can only take two different values, 1 or 0. It's defined over an event. So maybe we call it A. Then, so this indicator random variable is defined in this way. If A occurs, then it takes the value 1. If it does not occur, it takes 0, right? As I said, so here, what you're really interested in would be you wish to know the probability of event. So this event may depend on another random variable, y. When y takes different values, so the outcome could be different part in the event A, right? So in this case, so first, by using this indicator random variable, so first, because we discussed in the past, expected value of this indicator random variable is simply equal to the probability of A, right? So then, if we wish to think of the probability of A, then the probability of A is simply expectation of this indicator random variable. Indicator random variable is a random variable, right? So then we can use this result. As I said, so this A, whether A occurs, it may depend on another random variable y. So then this thing could be calculated in this way. Then we may discuss case by case, but just following the idea. Following the idea we introduced here. But now, by introducing this indicator random variable, so we can find out a probability of an event, right? So that's so that's the basic idea. Maybe I can show you an example, so that you can see how to do this. So here, so suppose we have two independent continuous random variables, x and y. So we wish to know the CDF of the sum of them. So suppose that we know the distribution of each of them, and we wish to calculate, we wish to know the CDF of the sum. So then let's see how to use this idea to calculate this. So first, maybe we use this f sub x plus y for the CDF of the sum, right? And by definition, this f sub this sum of z for any real number z should be the probability that the sum takes a value less than or equal to z, right? So then, how to calculate this? So this one is a probability, the probability of an event, right? As I said, it can be think of as an expectation of an indicator random variable. So indicator, so about this event, right? And here, so if you go over this, then from this result, then you can reach here. So the basic idea will be the same. We just discuss case by case. So here, we also use the same idea. We discuss case by case. So when y take different values, then what will happen, right? So then we wish to calculate this probability. Then we just take an integral over the real line. So at each point, so y takes a value over the real line, right? And when this random variable y takes this lowercase y, the corresponding PDF should be this, right? And again, the idea is still case by case and weighted by the corresponding probability or density there, right? So then this one should be equal to this guy. For this guy, it could be further simplified. So this one is y takes this lowercase y, right? Because y takes this value essentially, so this part is fixed. It's equal to this lowercase y, right? So this probability becomes this one. So this the value of y has been fixed. Because this y is fixed, then this probability can be written in this way. We just put this y to the right-hand side of this inequality. So x should take a value less than or equal to z minus y, right? It looks like that. And here, because x and y are independent, so you know something about y, it won't help you to know more or less about x. So this conditional probability should be equal to the unconditional probability, right? So what is this unconditional probability? It is simply, so the CDF of x at z minus y, right? So then here you can see that if you wish to know the CDF of the sum, it should be equal to something like this. It's an integral. So both the CDF of x and the density of y are involved, right? So this is the example how to calculate a probability of event. So this is something I wish to discuss about this conditional expectation. And actually, I think this conditional expectation would be a bit tricky. So this is the real tricky thing in probability theory. Conditioning, I would say, is the most important part of conditional theory, and that's something that is unique to probability theory, other than other branches in math. So this part could be a bit tricky, but later when we study Markov chain, then you should have more chances to practice this. But I think at this stage, you should be clear about conceptions about this conditional probability. So then, I think another thing I would like to mention a little bit is about this central limit theorem. So in the past, so several weeks ago, we discussed that central limit theorem, right? So maybe let's recall it. So central limit theorem is something like this. We consider a sequence of ID random variables. And because they have the same distribution, they should have the same variance and the same expected value, right? The expected value is mu, and the variance is sigma square. Then central limit theorem says something like this. So this expression, the probability that this expression takes a value less than or equal to x should be close to the standard normal CDF when n is large. So that's something we discussed in the past. Actually, if you remember what we discussed several weeks ago, you may realize that this expression looks a bit different from what we discussed in the past. Maybe let me check that. This is the central limit theorem we discussed previously, right? So this thing, as I explained, so this is the sample mean, right? So we take x1 over xn, and the sample mean of them is called xn bar. The sample mean, how did we explain central limit theorem weeks ago? I explained that in this way. So first, we know there's an important result called strong law of large numbers. Strong law of large numbers says this sample mean should converge to mu, right? But this sample mean, anyway, is still a random variable for any n, right? It's close to mu, but it's still different. It's still a random variable. If we wish to study the randomness in this sample mean, then if we just study this x bar n minus mu, then the randomness would be too small because they're close by strong law of large numbers. If we really wish to study the randomness there, we need to zoom in this randomness a little bit, right? So then that's why we need to have this factor of square root of n. When n is large, so this one is a large number. So this a small randomness times a large number will become a reasonably large random variable, right? And then central limit theorem says that something like this, so such a thing, when n is large, so the distribution of that is approximately standard normal, right? That is how I explained central limit theorem weeks ago. Now, this thing, actually, it can take a different form. The form is like this. I think I leave it to you to check. So those two forms are essentially the same. So I leave it to you. So now, it takes something like this. Then you may ask me the question, why? So this time, you review the same thing in a different form. Because this form, we have a different explanation. So here, we consider a sequence of IID random variables, right? x1, x2, and so on. For each guy, for each xk, what we did is that we remove the expected value of that first. Then a random variable after removing the expected value, then expected value of that will be 0, right? So xk minus mu is again a random variable, but the expected value of this guy is 0. So it means that it may take it could be bigger than 0, could be smaller than 0, right? Then maybe we can think of this xk minus mu over square root of n. Sk minus mu is a regular random variable with mean 0. But if divided by square root of n is a large number, then it would be a small random variable with mean 0. right? You can think of that as a small random effect. Again, this xk minus mu over square root of n can be think of as a small random effect. And then we have a lot of such small random effect. We have n such copies. We add them together. Then we have this thing. So the central limit theorem says that, so this guy has the sum of a lot of small random effects should follow a normal distribution. Right? That's another interpretation. So this interpretation is very insightful. Why I said so? Because you may realize that there'll be a lot of things that could be affected by small random effects. As long as such a value is infected by a lot of small random factors, then its overall behavior should be like a normal distribution. So that's why we can often see, so this bell-shaped curve appears everywhere, right? So maybe let me give you an example here. So this is the distribution of SAT score in America. So we have more than 1 million scores here. So you may know that the SAT score is just SAT is just a standard test for high school students. And each student need to sit there, answer many questions. So maybe multiple choice questions. So you can think that so his or her score would be the sum over many questions, right? So for each question, you may have a higher or lower mark. Then, because his or her overall score will be the sum of a lot of questions, then the distribution of such score will be affected by a lot of small random effects. So, as I explained just now, you will see this bell-shaped curve there, right? So that's an example. But you may say that. So this actually, the central limit theorem, the condition is pretty restrictive. So for example, it requires all those random variables must be IID, independent, they have the same distribution, right? So if we consider SAT score, of course, some questions are easier, some questions are more difficult, then the marks for each question may not be IID, right? But actually, this is just the simplest version of a central limit theorem. We have much stronger versions of that. So for example, there's another version like this. So this is in this version, we still have a sequence of random variables. We assume these random variables are independent, but they may not have the same distribution. So this is another version of central limit theorem. So we don't require the same distribution for everyone. Then we can still prove that under certain conditions, the standard normal will show up. And it is just another version. We have an even stronger version that does not even require independence. We can have a sequence of random variables. They may be dependent on each other. As long as the dependence is not so strong, they'll be fine. So that's why we can see this bell-shaped curve everywhere as long as data, so there are data involved, right? So this is the important insight from central limit theorem. I just summarize it here. So if a single measured value can be regarded, sorry, I missed a B here, can be regarded as the weighted average of a large number of small effects, then such a measured value should approximately follow a normal distribution, right? So this is another interpretation of this central limit theorem. Questions? So if no question, let's have a break of 10 minutes. Okay, let's move on. Maybe so. Let's first think of exercise problem like this. So here, suppose that we have 10 IID random variables. So each one has a uniform distribution over 0 and 1, right? Then we wish to know what is the probability that the sum of them is bigger than 6. So how to calculate this probability? So here, so first we may think of because the uniform distribution is pretty simple, then you may think of is there any way to find out the distribution of the sum of those 10 guys. Actually, I can tell you that it's even if the distribution of each one is simple, the distribution of the sum of 10 uniform random variables could be very complicated. So typically, it's beyond our capability. So then how to find out such a probability? Then the idea is to use central limit theorem, because it's a sum of IID random variables. Then in our minds, so after the so-called centering and scaling, then the standard normal should show up. So that's the idea. So now let's go over how to calculate this. So such a thing. So here we wish to calculate such a probability. So this probability x1 up to xk bigger than 6, right? And each x is just a uniform random variable between 0 and 1. And maybe let me remind you, so what is the expected value of a random variable, a uniform random variable, and what is the variance of that? So for uniform random variable over A and B, so the expected value of that should be just the center point, right? If you go back to check our lecture slides, you see, so it's there. So the expected value is just A plus B over 2. And the variance is B minus A squared over 12. So it's also there. So because each x is just a standard uniform, so then the expected value of that should be 1/2, and the variance should be 1 over 12, right? So then, as I said, so if we just wish to find out this probability, approximation of this probability, then we can think of a central limit theorem. The idea of central limit theorem is so because it's a sum of IID random variables, then we need to think of ways to make it close to a standard normal random variable, right? So how can we do that? So let's recall. So the central limit theorem is something like this, right? For each xk, so first we need to remove the expected value of that and take the summation, sum them up together, divided by standard deviation times the square root of n. So this thing should be close to a standard normal random variable, right? But so far, what do we have? It's just the sum of 10 IID random variables. Then we need to do some transformation so this guy will be transformed to something that has such a form, right? So then what we can do is just for each xk, we first need to remove the expected value of that. Expected value is just 1/2, right? Take the summation over sigma standard deviation. Standard deviation is the square root of the variance. So the square root of 1/12. And n is 10, so square root of 10. So this is this expression, right? Because of what we really need to know is the sum of them bigger than 6. If on the left-hand side, we just did some transformation like that, on the right-hand side, we need to do the same transformation accordingly so that we can still keep the inequality there, right? So then let's think of what we did now. So first, in the numerator, so for 10 guys, we remove 1/2 each. So totally, we remove 5, right? So this 6 should minus 1/2 times 10. And then, so this guy is divided by, so this number, square root of 10 times square root of 1/12. Then on the right-hand side, we need to do the same thing. So that's, what do we have? This. And then, as I said, when n is large, then, so this guy should be close to a standard normal. So then we just use a z, so z is a standard normal random variable to replace that. So then what do we have is, so this probability should be roughly equal to probability that z bigger than, so this thing. This thing in the numerator is 6 minus 5, which is 1. So should be something like this. And this one actually turns out to be square root of 1.2. So this probability should be close to the probability that standard normal bigger than square root of 1/2, right? So you may have, so now we have such an expression. Then you may ask me the question, how to calculate this probability? You go back to check the table, right? So if in the final exam, I give you a question similar to this, so then I should also give you a table. Then you check the table to find out the probability. And then another question is, so for the central limit theorem to hold, usually we require this n to be large, right? But here n is only 10. Is that large enough? So that's the question. So actually, I cannot say it's a sufficiently large or not, because it depends on how accurate such approximation should be. But for our purposes, as long as n is, say, larger than 10, tens of that, or even 100, 200, then we just assume it's sufficiently large. So as long as it's more than a few, I think, generally speaking, you can use this idea. So it's fine. So it's generally accurate. So that is so this problem. So, and also maybe I can show you some other examples that the bell-shaped curve will show up. So, for example, several years ago, I read this article from the Atlantic. So that the article shows the distribution of males and female in America. So that's you see this this blue one is the distribution of height of husbands, and this red one is the height distribution of wives. So we know that actually there could be a lot of factors that may affect a person's height, right? How tall you will be. So I think nobody can tell all the factors, nutrition, whether your parents are tall or short or whatever, right? So we don't know. We don't know all the important factors. But anyway, but we can tell that there could be a lot of factors there, because it could be affected by a lot of factors. So you see that the bell-shaped curve still show up, right? Of course, it doesn't look like a perfect bell shape, but anyway, it's similar to that, right? So that's a example. And so if we think of the difference, the height difference between husbands and wives, you can still find out something similar to a bell shape. So this, how can we affect this one? It's more complicated. It could be some culture issue or whatever, right? So this one could be even more complicated, but you can still see bell-shaped curve. So that's why it's everywhere, right? So I think you have time. You may check this article. It will be fun reading. And there's even a device, so which is designed to show central limit theorem. So this device is called Gordon's board. So what is that? The picture of that looks like that. So people just drop beads from the top. You see that there's a slot or vent here. So beads will be dropped from here. And you see that below the vent, so there are a lot of pins over different levels, right? So you can think of, so if I drop a bead here, so first I will hit a pin in the first level, right? So when it hits a pin at the first level, then maybe 50-50 will either go left or go to the right, right? Either left or right. Then, so this is only for the first level, and then it will reach the second level. So at the second level, it will hit another pin. Again, left or right. It's random, right? Then the next level. So you see that when a bead drops, it will go through a lot of levels. At each level, I will choose either left or right, randomly, right? So then, until a bead drops into a cell. So you see that because each bead will go left or right. So then, randomly. So in the end, so there will be a lot of bees. If we drop a lot of bees there, then for those cells close to the center, so they will have more bees there. For a cell that is away from center, far away from center, if a bee will go there, so for example, it will need to go left, 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 left. So the probability will be small, right? So then if you drop a lot of bees, you could expect that for such cells, you will not see a lot of bees, right? So because of this mechanism, then you drop a lot of bees there, gradually you'll see a bell shape will be there, right? So that's a very smart device for this for you to understand this central limit theorem, right? It's called Gordon's board. Actually, I have one here, so I'm not sure whether you can see it. So let me stop share. How can I make this a full screen? A bit too small. Okay. Can you see it? So you see there are a lot of bees here. If we put it down, so you see the shape is there, right? So do it again. So that's amazing, right? So I will put it here. So after class, if you wish to play it, you can come and play. Actually, so you can. I bought it from Amazon. So if you wish to have one, you can also buy it there. I think that's everything I wish to discuss about this conditional expectation and central limit theorem. So that's the end of this lecture. Okay, so let's start a new topic. So it's about simulation. So basics of Monte Carlo simulation. So first, what is simulation? I think all of you may have some idea about simulation. Simulation means that if we wish to study a system, it could be too expensive for us to build up such a system. even a simplified one, it could be expensive. Then, thanks to the development of modern computing devices, we have more and more powerful computers, more and more powerful softwares. So then we may use, when we design a computer program to mimic the process of a procedure or the operations of a system and so on. Then we use a computer system to mimic the process, and as long as we have some output from the computer program, we just believe that it should be close to the reality. So then we will analyze the output from the computer instead. So such a process is called simulation, right? So then to motivate this, maybe let's discuss a very famous Monty Hall problem. Actually, this problem is a bit intriguing, but I would say it may not be a very good example for using simulation. But because this example is so intriguing, so that only when people did some simulation, then people realized that they began to truly understand this problem. So that's why I wish to introduce this simulation by using this example. So what is this Monty Hall problem? It's I think maybe some of you already know something about it. It's like this. Suppose that on a game show, you are given the choice of 3 doors. You need to choose from 3 doors. So among those 3 doors, behind one of them is a car. For the other 2, goats. So which means that if you open the door, if there's a car behind that, you will have the car. Otherwise, you will have a goat. Of course, you wish to have a car, right? So then, suppose that before the doors open, you pick one. Say, door 1. So then, the host, who knows what are behind the doors, open another door. So which has a goat, right? So now keep in mind, so there's 3 doors. One has a car, the other 2 have goats. You select one, which means that for the remaining 2, at least one of them will have a goat, right? So the host can always show you a goat in this setting. Then after the host shows you a goat, he gives you an option. Do you wish to switch? Originally, you select door 1. Then the host show you that behind door 3, there is a goat. Then the question is, do you wish to change from door 1 to door 2? It gives you that option. Then the question is it to your advantage to switch your choice? So this is the so-called Monty Hall problem. So for this Monty Hall problem, actually, I would recommend you reading the Wikipedia page of that. So this is you will see it's a a very detailed story of this problem. There are a lot of famous mathematicians, smart people, and mass media involved in this problem. Why is so? Because it was so intriguing at the time. So why is so intriguing? Because actually, if you think of this problem, so there are two opposite opinions. So both intuitions would seem reasonable. So for example, the first intuition would be like this. So after the host reveals a goat, you now have 1 in 2 chance of being correct, right? So as I said, so there are 3 doors. You pick one. And for the other 2, there must be at least 1 goat, right? And the host show you a goat. Then you're pretty sure that among the remaining 2 doors, there is 1 goat and 1 car, right? Because you already select 1. So which means that, so the probability that, so behind that door should be 1/2. Because, so this one is 1/2, the other one is still 1/2. No need to switch. Things will be the same. So that's one intuition. Another intuition will be like this. So when you select the door, because you have no information, for you that you have only 1/3 chance, so you will have a car, right? Before the host show you when all doors are closed, then the chance that you have select a car will be 1/3, right? Then, because the host can always show you a goat, right? So the host knows what is behind the door, right? So he shows you a goat. Then in this case, the chance that the other one not shown by him, not selected by him, so after he reveals the goat, the chance that the car is behind the remaining one should be 2/3. That's another argument. So it's just like this. Originally, the car has a 1/3 chance of being behind your pigs, and a 2/3 chance of being behind one of the other 2 doors, right? The host opens the door, so the chance for the 2 sets don't change, but the chance that move to 0 for the open door and 2/3 for the closed door. In this case, so if you switch, then your chance will be increased from 1/3 to 2/3. So that's the argument why you need to switch, right? So this is the 2 opinions. So both opinions may seem reasonable, or at least plausible to some people, right? But the question is, which argument is correct? So, as I said, a lot of people felt confused about this problem. And in my impression, I would say majority of people believe the first one is correct. But indeed, the second one is correct. So the answer is that you should switch. So when I first knew this problem, so I also believed that the first one should be correct, but I was wrong. The answer should be should be the second one. But the thing is, the first one is at least, it seems, at least, so I think nowadays, I still believe that it's the first explanation is very intuitive, even if it's intuitive but wrong. So, but the thing is, how can we tell that this one is not correct, right? So then, how to tell this? So maybe to think of this problem in a more careful way, so we need to, before we proceed, so we need to specify all the assumptions in a very clear way, so that in next steps we can discuss so in details. So first, let's assume something like this. I think all those assumptions are pretty reasonable, and some of them has already been explained when I introduced the problem. So in this setting, so we know that you first pick a door, right? And then we need to assume that the host must open a door that was not picked by you. Otherwise, it doesn't make sense, right? So otherwise, it's not interesting. So this is just like, it seems like a trivial assumption. The second one is that the host must open a door to reveal a goat and not the car. So which means that if you picked one, but the host opened a door and behind the door is the car, then it just tell you that you're wrong. Then the game is over. It's not interesting, right? Because we know that there are two goats, just one car. So the host always have the possibility to show you a goat. So which is he will always to do so. And also the third assumption is that the host must offer the chance to switch between the originally chosen door and the remaining closed door. You can give the chance that you can switch. So that's the three assumptions we need to make. So that's so as long as so we assume those three conditions, then we can discuss what will happen, right? So then. What do we need to do? As I said, I wrote a MATLAB program to simulate. So this is a very simple process. So this multi-hole problem. So maybe I can maybe let me briefly introduce several commands in MATLAB, so that when I show you the code, then you can understand what's going on there. So in MATLAB, the command rand, R-A-N-D, actually, it will give you a random number that is uniformly distributed in 0 and 1. It's a standard uniform random number. This is rand. And this R-A-N-D-I, this I for integer. So n, it will return a random integer from discrete uniform distribution from 1 to n. So the probability that it's any integer from 1 up to n is 1 over n. So this is another command. And this RANDN, this n for normal, it will return a standard normal random variable. So those three commands are mostly used in MATLAB when we do Monte Carlo simulation. So now let me show you. So actually, so this is a online MATLAB terminal. Actually, it is not really MATLAB. It's Octave. Octave, you can think of Octave that's as an open source version of MATLAB. So this is my code. You see that it's pretty simple. So this code in this program, what I did is to run the Monty Hall problem 1,000 times. 1,000 times each time. So I will count. If you don't switch the door, whether you will get the car. If you switch the door, whether you will get the car, right? So if we run it for 1,000 times, then we can just compare. If you switch, how many times you will receive the car. If you don't switch, how many times you will receive the car. Then you can tell which one is better, right? So that's the idea. So I think the code is pretty simple. And so the idea, as I explained, I just ran that for 1,000 times. And I think after the class, I will post the code on Canvas. So you can check that. I think the explanation there is also very detailed. So I just don't bother to explain everything here. Maybe I just ran it. So here you see that. So among those 1,000 runs, if I don't switch, then the relative frequency of getting a car is this. Among those 1,000 times, 329 times I will have the car. If I switch, then 671 times I will receive the car. Actually, because this is random, you see that, so the first number is very close to 1/3, and the second number is very close to 2/3, right? So from this simulation, you can see that actually it's to my advantage if I switch, right? So then, which means that the second intuition is correct. If you don't switch, the chance is still 1/3. If you switch, it will become 2/3. So if it's still not convincing, maybe let me run it again. So this time, because each time is random, this time among the 1,000 runs, I have cars in 320 times. For the remaining 680 times, I will receive a car if I switch, right? So it's the third time is so the relative frequency is different, but you see it's still around 1/3, 2/3. So this is so this is the how to simulate this Monty Hall problem. Actually, it's not difficult. And as I said, so please spend some time reading the code after class. I think I would emphasize that. I think I said at the beginning of this course that in the exam you are not required to write code. But I still feel that it's necessary for you to understand some programming techniques. So it won't be tested for using the MATLAB language, but some basic conceptions, techniques for simulation will be tested, but no coding. So actually, so this problem It's not really a difficult problem because if you wish to analyze that by using a tree diagram, so you will see that this problem, even if it's intriguing, but it turns out that it's a pretty simple problem. So then maybe let's analyze this Monty Hall problem by using this tree diagram. So then I think you will see that very clearly. So first, we know that before the host show you a goat, you just pick one, right? You just pick a door. So at this time, the chance that the car is behind the door is just 1/3, right? So because we assume that you selected door 1, so then the probability that the car behind door 1 is 1/3, behind door 2, door 3, or 1/3, right? So that's the first level of this tree diagram. So next, the host will open the door, which means that you will have an extra piece of information. After you get this information, then probability will change into conditional probabilities, right? So then let's discuss case by case. So as I said, the car could be behind any of the doors, each with the probability 1/3. If the car is behind door 1, if the car is behind door 1, means that there is a goat behind door 2 and a goat behind door 3, right? Then the host can open any of them. So maybe we just assume he will open one of them at random, 1/2, 1/2. So with 1/2, it will open door 2, show you a goat. With 1/2, it will open door 3, show you a goat, right? So in this case, you see that now, so the probability at this stage would be 1/3 times 1/2, which is 1/6. Here also 1/6. In this case, we know that because the car is behind door 1, if you don't switch, you will get it. If you switch, you will get a goat. You will get a goat, right? So you'll see, if you don't, in this case, if you don't switch, you will get the car. If you switch, then you get a goat. So let's discuss the second case. So in this second case, the car is behind door 2. The car is behind door 2 because you already selected door 1. You select door 1, the car is behind door 2 because the host can only show you a goat, which means that the host will always open door 3 with probability 1, right? So in this case, you see that if you don't change, you don't switch, you'll receive goat. If you change, you receive a car, right? So that's the second case. And the third case is exactly the same as the second case. So the car is behind door 3 because you already chosen door 1, then the host will open door 2, right? In this case, so if you switch, you will have car. If you don't switch, you will have goat. So that's all possible cases. So now let's just calculate probabilities. If you don't switch, then in this case, you will have car. The probability is just 1/6 plus 1/6 is 1/3, right? And so if you switch in this case and this case, you receive a car. So the probability is 1/3 plus 1/3. That's 2/3. Right? So this is just a multi-Hall problem. So you see that if you just analyze that step by step in a very standard way, then it seems very simple. But if you just believe your intuition, then it becomes very intriguing. So that's this multi-Hall problem. Okay, so I just wish to use this as a very simple motivation of simulation. And next week, I think we will discuss the basic simulation techniques, random Monte Carlo simulation, random number generator, and so on. But for this week, I think that's it for today. Questions? If no questions, let's meet next week. Thanks.